Hello, welcome to my channel. I'm Bukola Joseph, the physics enthusiast. So we are going to be solving a problem on statistical physics. Please stay tuned and see how we'll solve this problem. Let me read the question and then we'll tackle the problem together. So, show the possible arrangement of two indistinguishable particles, m is equal to n, among three energy states. Assume the particle obeys Bose-Einstein distribution to calculate the weight of their configuration. So now this is a problem on Bose-Einstein. But before we solve this problem, let's quickly talk about the characteristics of Bose-Einstein. I'm going to be talking about four characteristics. Now, the first characteristic we're going to be talking about is the fact that any of the particles can be in a state that is 0, 1, 2, 3, 4, blah, blah, blah. Then two, the particles are indistinguishable. The particles are indistinguishable. Indistinguishable. Okay, what does that mean? It means they cannot be differentiated. Okay, they cannot be differentiated. Then the third characteristic is that the particles are symmetric with respect to interchange. Okay, with respect to what? Interchange. Then the fourth characteristic is that they do not obey the Pauli's exclusion principle. So now, what is the Pauli's exclusion principle? The Pauli's exclusion, let me write it on the board. We have Pauli's exclusion. Pauli's exclusion principle. What does the Pauli exclusion principle state? It states that no two fermions, okay, particles like proton, electron, neutron with half integer spin, okay, with half integer spin, integer spin can occupy the same quantum state simultaneously. So that's the Pauli's exclusion principle. It states that no two fermions, okay, with half integer spin can occupy the same quantum state simultaneously. Now you'll be like, what is the use of this law? What is it? Like you hear some people, let's apply this thing now. This principle is supposed to be applied. Enough of all this theory. Let me tell you, guess what? This principle is applied, okay? It is an applied principle even till today, okay? This principle has helped in the structure of atom, molecules, and solid. And of course, this principle was formulated by, what's that name again? Wolfgang, I don't know if I'm pronouncing it well, Wolfgang Pauli. Okay, Wolfgang Pauli is an Austrian physicist. Okay, and he formulated this principle in the year 1925. We're in 2025. That's like 100 years ago. Enough of history. Let's solve this problem. So now, going by the question we have on the board, the first question says that assume the particle-based Bose-Einstein distribution. Calculate the weight of their configuration. Now the question says show the possible arrangement. So we have been given three energy states. So we have solution. So three energy states, say 1, 2, 3. Okay, so we have m is equal to n. This is the particle. Okay, it doesn't obey Pauli's exclusion principle. So it means we can have mn here, then dash dash. Then we have dash. We can have them here, then dash. Then we can have them here. Okay, or it can be like this, and then it can be like this. Okay, and then we can, where is the next one? It can be like this. So if we are to count the number of ways, it means we have 1, 2, 3, 4, 5, 6. We have 6 ways of arrangement. Okay, so this is your answers. These 6 ways of arrangement. So we have been able to show the possible arrangement of two indistinguishable particle equal m is equal to what? N. So we are going to solve the next question. This next question says that we should calculate the weight of their configuration. So now to calculate the weight of configuration, we are going to be using a formula. Okay, it has a formula, and this formula is this. We have W is equal to GJ minus 1 plus NJ factorial all over GJ minus 1 factorial, then NJ factorial. Now, GJ is the energy level and it is given. So we have GJ is equal to 3 and N is the occupation number. NJ is the occupation number, and we have 2. So we are going to substitute GJ, NJ in this question, in this formula. So we have W is equal to GJ is what? 3 minus 1 plus what? NJ is what? 2. Close the bracket, factorial all over. What is GJ? GJ is 3. We have 3 minus 1 factorial. NJ is 2. So we have 2 factorial. So let's simplify what we have. Okay, so we have 3 minus 1 is 2, right? 2 plus 2 is 4. So we have 4 factorial all over. So 3 minus 1 is 2 factorial. And then we have another 2 factorial. Let's further simplify. 4 factorial is the same thing as what? 4 times 3 times 2 times 1, right? 2 factorial is the same thing as 2 times 1, then dot 2 times 1, right? This is equal to what? 4 times 3 is equal to 12. 12 times 2 is equal to 24. 24 times 1 is 24 all over. 2 times 1, 2. 2 times 2, 4. 4 times 1, we have what? 4. So we have this. You can just simply 24 divided by 4. Okay. But if you can do it one step at a time. 2 here, 2. 2 here, 12. 2 here, 1. 2 here, 6. So we have 6 ways. Even so, the weight of configuration is equal to 6. Okay, is equal to 6. Okay, so I hope you enjoyed today's problem on statistical physics. Follow us for more. I'm still Bukola Joseph, the physics enthusiast. Bye.